Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I would like to thank all of you for attending today's webinar with MetaGeek. Today's host, Joel Crane, will be presenting today. And if anyone has any questions, feel free to submit them in the question box, and Joel will answer them at the end of today's presentation. Joel, I'm finished for now. Thank you so much for being here today, and the floor is yours to take over.
Great. Thank you, Julie. Welcome to Packet Analysis with IPA and AirPCAP NX. Just kind of a quick introduction. My name is Joel. I take care of all training functions here at MetaGeek. I also help out with support and things like that. We're a fairly small company, so we all wear a lot of different hats, and it's a lot of fun. After this webinar, if you want to learn more about Wi-Fi in general, one thing I'd encourage you to do is to check out the CWNP program. I hold several certifications from the CWNP program. It's a great way, a vendor-neutral way to learn more about wireless, and I'd strongly recommend checking out that program, especially the CWNA. That's the Certified Wireless. The Certified Wireless Network Administrator. That is a great certification to start with. And then if you want to dive more into this packet analysis stuff, which is the subject of this webinar today, the CWAP is also the study guide for that is available on Amazon. Excellent resource. And of course, be sure to jump on Twitter. If you're on Twitter, that's a great way to get plugged in with the wireless community to learn more about wireless in general. I would say probably about 50% of what I know is from things I've learned just by watching the wireless community on Twitter and learning from all the gurus that like to hang out there. So I'd strongly recommend that. Now, today's webinar, we're going to take a look at packet analysis, specifically packet analysis with IPA, and we'll talk about a few different things. We'll talk about the different types of interference that you'll encounter in Wi-Fi. We'll talk about the half-duplex nature of Wi-Fi, which is kind of the cornerstone, the building block of Wi-Fi, and then after that, we'll take a look at some of the specific types of packets that you'll see in wireless, and then we'll spend some time playing with IPA and actually looking at what a packet capture looks like live in our environment here. So with that, let's go ahead and get started. Now, I cover this concept in most of the webinars that I give because it's really the cornerstone, the building block of Wi-Fi, and that is the half-duplex nature of Wi-Fi. Now, this is important if you're doing spectrum analysis, and it's really, really important if you're doing packet analysis, because packet analysis completely revolves around this concept. And that's the concept that since Wi-Fi is half-duplex, that means that only one Wi-Fi device can talk on a channel at a time. Now, to stop and think about what exactly is half-duplex, let's think about what full duplex is for just a minute. Now, with a full duplex connection, we're able to send traffic in two directions at the same time. I'm sure that a lot of you are familiar with Ethernet, and with an Ethernet cable, we've got multiple twisted pairs of copper inside each cable, and that allows us to send traffic in two directions at the same time. It's kind of like a two-lane highway. With a two-lane highway, we can send traffic east and west simultaneously. That's a full duplex connection. Now, kind of an example, though, of a half-duplex connection is a conversation between you and a friend. In fact, a conversation, a human conversation, is very, very similar to Wi-Fi. Let's say that you're having a conversation with a friend, and you say something, and your friend says something at the exact same time. You're both going to cancel each other out. Only one of you can talk at a time. The exact same is true with Wi-Fi. If we've got a couple of wireless devices like this access point and this client device, which is just a laptop, if those two devices are on the same channel and they try to talk at the same time, they're going to cancel each other out. That is a half-duplex connection. So what does a typical wireless conversation look like? Well, every wireless conversation kind of goes like this. Let's say that we've got an access point and it needs to send some data to this client device. The access point is going to do a clear channel assessment. It's going to check to see if anything's talking on the channel, and then if there's nothing talking, it's going to take that opportunity to transmit its data to the client device. The client device is going to take a look at that data. It's going to pull up the magnifying glass and take a look at that data and make sure that it understood that data, and then it's going to reply with an acknowledgement, and that says, yep, check, I received the data. Now, there's a couple of things that can go wrong here. Let's say that the access point starts to transmit that data, but for whatever reason, it gets kind of garbled up before it gets to the laptop, and the laptop isn't able to understand it. If the laptop can't understand the data, it's not going to transmit an acknowledgement to say, yes, I received that data. Now, the next thing that's going to happen is that access point is going to start wondering, okay, well, I never heard an acknowledgement, so the laptop must not have received the data. So it's going to retransmit that data. It's going to keep trying to send that data over and over and over until finally the data makes it through and the laptop can go, yep, check, I received that data, and it can transmit the acknowledgement. Now, there's lots of different things that can interrupt this signal. Maybe the laptop is just too far away from the access point. Maybe something else started talking and interrupted that, or maybe there's some background noise, so the laptop just wasn't able to understand that clearly. There's lots of different things that can cause retransmissions, but any one of those factors can cause them. Now, when we're thinking about the half-duplex nature of Wi-Fi, we also need to think about it not just from a device-to-device basis, but on a channel-wide basis. So remember, the rule still applies even if we've got lots and lots of devices on a channel. For example, let's say that we have this Android phone, and this Android phone is currently transmitting some data to this access point. While that data transmission is occurring, all of the devices on that channel have to be quiet and wait for their turn to talk, even the access point. And this includes neighboring networks as well. If you've got a neighbor that's got networks, and if they're on the same channel, if they've got devices on the same channel, you also have to take turns talking with those devices as well. Only one device can talk on a channel at a time. And the more and more devices you throw onto a channel, the smaller and smaller everyone's opportunities to transmit gets. We'll come back to that in just a moment. We also have to think about how slow devices will affect the half-duplex nature of Wi-Fi as well. So for example, let's say that our Android phone here is using a nice fast data rate. It's transmitting at 54 megabits per second, so it's using a nice fast data rate in its conversation with that access point. But then we've got another device here. We've got another Android device here that's kind of on the fringe of this coverage area. And since it's so far away from the access point, it's had to slow down and use an older, slower data rate to make sure that the access point can understand what it's trying to say. So our one Android phone here, we're seeing 54 megabits per second. That's the fastest 802.11g data rate available. And then we've got this fringe device that's slowed all the way down to 1 megabit per second. That data rate goes all the way back to 1997 when the original 802.11 standard was created. That's the original data rate all the way back from 1997. The problem here is that this device is kind of like the slow kid in the back of the classroom. It talks very slowly, so it makes everyone wait for it to finish talking. This device is going to take 54 times longer to transmit the same amount of data as the device that's talking at 54 megabits per second. He's just like the slow kid in the back of the classroom. You know who I'm talking about, right? There's that one person in the classroom that they raise their hand really slowly and they say, teacher? Yeah, I had a question. It's like, hey, you know what? We're paying $100 an hour to be here or whatever, right? Spit it out, ask your question so we can get back to our class, right? That's what a slow device does. That's what a slow device does, is it consumes more airtime because it takes longer to transmit the same amount of data. And that's one of the main reasons why we want to keep fast data rates and keep devices talking quickly. So there's three types of interference that we have to watch out for. The first type is co-channel interference. Now this occurs when we've got devices that are on the same channel. For example, we've got an access point, we've got a few client devices, we've got neighboring client devices. All those devices on the same channel are going to compete for time to talk. And as long as there aren't too many devices on the channel, and as long as everyone's talking reasonably quickly, that's not a problem. However, there will become a point on the channel where things are talking too slowly, or maybe where you just have too many devices on the channel that all need to talk. Remember, only one device can talk on a channel at a time, and if there just isn't enough opportunities for everybody to talk, that's when we get co-channel interference. The next type of interference is called adjacent channel interference. Now, this happens when we have networks that are on partially overlapping channels. This is why we always want to use channels 1, 6, and 11. Networks that are on partially overlapping channels, instead of politely taking turns like co-channel, partially overlapping channels are just simply going to yell and scream over each other. They're going to interrupt each other, which is going to cause retransmissions, which is going to eat up more time on the channel. You see where this is going. It's very, very bad, and we want to avoid adjacent channel interference at all costs. Finally, there's non-Wi-Fi interference. We all know that the 2.4 and 5 gigahertz bands are shared with more than just Wi-Fi devices. There's tons of non-Wi-Fi devices there. Think microwave ovens, cordless phones, wireless video cameras, baby monitors, security systems, Xbox 360 controllers, Bluetooth devices. Non-Wi-Fi devices also need time to talk. They need to be able to get on the channel and say what they want to say. The problem is that non-Wi-Fi devices, well, they don't have any of those politeness mechanisms built in that Wi-Fi devices do. And so they will simply get on a channel and flood the channel with a bunch of basically incoherent garbage that Wi-Fi devices can't understand. And when that happens, Wi-Fi devices will simply back off indefinitely and wait for that device to finish talking. So today we're going to talk about packet analysis. And packet analysis is best for troubleshooting co-channel interference issues. If you look at a channel and see that a channel is just overloaded, a very, very busy channel, packet analysis will show us the details about all of that 802.11. That means Wi-Fi congestion on that specific channel. With packet analysis, we can basically view those conversations between laptops and tablets and smartphones and access points and any other devices that are on those channels. So what does a troubleshooting process looks like? Well, when I'm troubleshooting Wi-Fi, I always like to start with the physical layer. Now, if we were troubleshooting Ethernet, that would mean look at the cable. Is the cable good? Now, maybe you would test the cable with a fancy cable testing tool like a NetScout Link Sprinter or something like that, or maybe you would just simply replace the cable. That's the first thing you'd want to do is check the cable. Now, in Wi-Fi, the cable isn't a cable, it's wireless. The cable is RF. And so the first step that I always like to take is to look at the spectrum. I like to do spectrum analysis, and I use that to guide me to the next troubleshooting step. So if I look at the spectrum, I'm going to see one of these two things. Maybe I'm going to see a non-Wi-Fi signature. Now, if I see a non-Wi-Fi device, no amount of packet analysis is going to help me out with this. That's non-Wi-Fi. A packet analyzer won't understand that. It's just going to be noise to the packet analyzer. It's not going to tell me anything about it. If I see a non-Wi-Fi signature, then I'm going to use spectrum analysis. That's looking at layer 1. That's the raw radio frequency activity. I'm going to use spectrum analysis to identify and remove any non-Wi-Fi interference. Like, for example, I might identify this and go, hey, that looks a lot like a cordless phone, and then I might physically track that down and get rid of that because packet analysis isn't going to help me out there. On the other hand, though, I might see a Wi-Fi signature. And that's the second thing I might see is a Wi-Fi signature. If I see a flat tabletop shape like this, this is a shape that 802.11g and 802.11n make in the spectrum. And if I see that it has very, very heavy utilization, in this case, I can see that it's keeping the channel busy about, I'm going to say, judging just by looking at it, about 80% of the time or more, then I know that that channel is very, very busy, and I know that that is from Wi-Fi activity. That's what I'm going to use packet analysis, that's looking at layer 2, to dig deeper into that Wi-Fi congestion to figure out what is going on. So that's kind of the split that I make. That's the decision tree that I use to decide what I'm going to use next. So here's the difference between spectrum analysis and packet analysis. With spectrum analysis, we're looking at layer 1. That is the raw radio frequency activity in the band. Spectrum analysis shows us the sum of all of the radio activity on the channel. So that's all of the radio activity combined. That could be 3 or 4 different Wi-Fi devices all talking. Since we're just looking at the shape of it, we know what it is based on the shape. And in this case, I know it's Wi-Fi. And we can see how often they're talking, how busy they're keeping the channel. And that's called utilization in the spectrum analysis world. With packet analysis, that's moving up to layer 2, we're actually going to decode all of that activity. Instead of just looking at the radio waves, we're going to decode that, and that's going to show us the details of all of the 802.11 congestion on that channel. Think of it like this. Spectrum analysis shows us the raw radio frequency activity. It basically shows us a bunch of radio waves. With packet analysis, we're actually going to look at those pieces of information that those 802.11 devices are passing back and forth between each other. That's the difference between spectrum analysis and packet analysis. So let's start to dig deeper a little bit now into the different types of frames that we'll see in wireless. Now, I recently had an epiphany where I realized that using the word packet is actually kind of incorrect. If we're thinking about packets, we're really thinking about something that's being moved around on a packet switch network like Ethernet. Now, you can call them a packet. A lot of people call them packets, but really the more correct term for them is a frame. So think of in wireless a frame and a packet, really the same thing. frame is probably more technically correct, but it's okay to use either of those terms interchangeably. Now, there's 3 different types of frames, and they all perform different functions. There's management frames, control frames, and data frames. And one really fun thing that we do in IPA is we assign a unique color to each different type of frame. So if you don't remember what the colors mean, in IPA there's a really slick little drop-down menu that's built in. I'll show you where that is. This is that drop-down menu. You can use that to remember what type is what and what color is associated to which. So let's go through each one of these one at a time, and let's learn what they do. We'll start out with management frames. Now, management frames are pretty simple. They help manage stations joining and leaving wireless networks. In other words, they help stations get on a network and get off a network again. So the first type of management frame is a beacon. A beacon is simply an access point's announcement that it exists. So an access point will continually, every 104 milliseconds or so, it'll just simply say, hey, I'm Joel's network. I'm here. I support these data rates. I support this type of encryption. And then it will repeat itself over and over and over again. Hey, I'm Joel's network. I'm here. I support this type of these data rates. I support this type of encryption. When you get your phone out of your pocket, maybe you go to a friend's house and you want to connect to their Wi-Fi to avoid chewing up all the data on your data plan. You get your phone out of your pocket and you open the Wi-Fi list and you'll see a big list of wireless networks. In fact, we could do that on my Mac right now. If I go up here and click on the Wi-Fi menu, we can see all of these different networks that are nearby. That's because of beacons. Our Wi-Fi adapter is hearing all of those networks that are beaconing nearby, like PTMC and Forsta and AirNet, and all those different networks that are nearby. So that's what a beacon does. Now, the next type is a probe. A probe is kind of the opposite of a beacon. When you connect to a network, your computer stores the information for that network. It basically stores a profile for that network. Like, for example, I've connected to MetaGeek, and so my laptop remembers MetaGeek. Now, whenever I leave the MetaGeek network, if I maybe I pack up for the day and head home, at the end of the day when I do that, and I leave the MetaGeek office, my phone will basically lose contact with the MetaGeek network and it'll fall back on cellular like it normally does. But then it will start probing for familiar networks. It'll start going down the list looking for familiar networks. It'll say, hey, Joel's network, are you there? Hey, MetaGeek, are you there? And it'll just go through the list over and over and over again, probing for networks. That's called a probe request. So here's an example of a probe request. It's kind of cut off right there, but there's a probe request right there. And then any access points that are nearby might answer with a probe response. So maybe when I come back in the morning, tomorrow morning when I come back to the office, I'm coming up the elevator and the elevator door's open. My phone is going, hey, MetaGeek, are you there? And then MetaGeek will reply, yes, I'm MetaGeek, I'm here. And then we can start the process of my phone joining that network. So that is called a probe. Is kind of the opposite of a beacon, and it helps us get associated to a network faster. Now, the 2 other types of frames here are authentication frames and association frames. Those are basically just are part of the process of us joining the actual network. When we fire off an authentication frame and follow up with association frames, that's part of the process of devices actually joining the wireless network. Now, the next type of frame type is a control frame. Control frames control the RF medium, and they aid in the delivery of other frames. Basically, they make sure that other frames get delivered. And one of those is called an ACK. We actually saw this earlier when we were talking about that process of data and then acknowledgement. Data and then acknowledgement. It's just like a TCP/IP ACK, except instead of happening at layer 3 and above, this is happening at layer 1 and 2. And in Wi-Fi, we'll send our data and we'll receive an ACK to say, yes, I received that data. Now, there's another type of ACK called a block ACK, or a block acknowledgement. Now, here, instead of having to go data, acknowledgement, which is kind of slow, with a block acknowledgement, we can go data, acknowledgement. Data, acknowledgement. We can acknowledge a block of frames all at once, and that helps us preserve airtime. Then there's a request to send and a clear to send. I wish we had more time to get into exactly what request to send and clear to send does, but basically this helps us make sure that client devices don't accidentally talk over each other. If you've got a couple of client devices that are both connected to the same access point, but those client devices can't hear each other and they're having a hard time not talking over each other, then we'll implement implement RTS, CTS, request to send, and clear to send to make sure that our devices have to ask for permission to send before the access point will say, yes, you are clear to send. The trick here is that clear to send alerts everyone else on the channel that can hear the access point. Hey guys, shut up. There's a conversation that's occurring here. You need to be quiet for this amount of time. So that's what RTS, CTS does. Now the next type of frame, this is kind of the whole reason why we have wireless networks at all, are data frames. What do data frames do? Well, they help carry higher level protocol data. They move the actual data around. Now there's 3 different types of data frames. There's a data frame, pretty self-explanatory. And then there is a quality of service data frame. A quality of service data frame will help us prioritize certain types of traffic. So for example, one thing that we're doing right now is you're hearing my voice basically through the internet, through IP. It's essentially a voice over IP connection. Voice has to be delivered in a very, very consistent very consistent and reliable way. I mean, if I'm talking to you and a few packets that are carrying my voice get dropped or get delayed or arrive out of order or something like that, that's really bad. My voice starts sounding like a robot when that happens. Quality of service helps us fix that, because now we can say, hey, this traffic here from this other user, they just want to get on Facebook or something like that, we're going to hold off on moving that data for just a minute. We're going to concentrate on prioritizing this voice data, or maybe this video streaming data, or this video call data or something like that. That's what quality of service does, is we can prioritize certain types of data. Now, the last one is kind of a funny one. Null data, it's not really a data frame at all. These really carry things like power save polls, so they're not actual data. I just don't think they had anywhere else to put them, so they ended up getting thrown here in the data section. So they're not truly data. They're just used for things like power save polls. For an example, a Wi-Fi device might transmit, hey guys, I'm going to sleep for this much time. Check back with me in 3 seconds or something like that. I'll wake up again and I can receive any information that you have from me. So that's what a null data frame does. Okay, so how do devices decide who gets to talk next on the channel? If we've got a bunch of devices on a channel, and if they all have to take turns talking, how do we decide who gets to talk next? We do it with this airtime arbitration process. I'm going to move quickly through this, so glue your eyes to the screen and listen carefully, and we'll go through this real quick here, but just pay attention because it's kind of complicated. This kind of makes me amazed that Wi-Fi works at all. So what we've got here is we've got time moving in this direction. So moving left to right here is time, and then we've got a bunch of different wireless stations represented here. Now remember, a wireless station can be an access point or a client. It doesn't matter which one it is. It's one or the other. So we've got station 1, station 2, 3, 4, 5, and 6. So we've got all these different wireless stations with time moving from left to right. So let's say that station 6 is just finishing up sending some data, and then station 5 is going to reply with an acknowledgement to say, yep, check, I received that data, I got that data, we're good to go. Now, both station 2 and station 4, they both want to talk. They both have something that they need to say. So they're going to essentially roll the dice to decide who gets to talk next. So station 2 rolls a 7, and station 4 rolls a 9. And so now they have decided together that, okay, it's station 2's turn to talk because it rolled a lower number. So they've decided who is going to get to talk next. So now, station 2 is going to transmit a request to send. It's going to ask the access point, hey, am I clear to send? And then, so it's going to transmit that request to send, and that's going to let station 4 know, hey guys, we're talking, you didn't get that chance to talk now. It's actually station 2's turn to talk. Then station 1 is going to transmit a clear to send. It's going to say, yes, you are clear to send, and that alerts everyone else on the channel that there's a conversation occurring. Everything else on the channel is going to set a NAV timer. It's a network allocation vector timer, basically a timer that they're going to set. They're going to synchronize their watches and say, okay, collectively, we are all going to shut up for this amount of time. So they all set that timer and be quiet. Now station 2 is going to transmit its data, and station 1 is going to reply with the acknowledgement, and that's it. They have used up all of their time that they had to talk, and so that conversation is now over. So now remember how station 4 wanted to talk, but it didn't get a chance to. It rolled a 9, but it got ruled out by station 2, which rolled a 7. So that means that station 4 now has a 2 remaining. It's got 2 back-off slots remaining. So station 2 has more to say, so it's also going to roll. So this time it rolls a 10, but station 4 has only 2 left. So station 4 automatically gets the chance to talk now. So now it's station 4. So when station 4 transmits its data, it's not using RTS, CTS, it's going to transmit its data, and that lets station 2 know, hey, something else is talking right now, and then station 3 replies with the acknowledgement. And the crazy thing about this is that this is happening. If you have a cell phone in your pocket right now that has Wi-Fi on, this is happening several million times a second in your pocket. It's very, very fast. And I don't know about you, but once I had this explained to me, I stopped complaining about Facebook pages loading really slowly because it's amazing. It's really cool. So how do we visualize this whole thing? How do we understand what's happening in our wireless environment? Well, the old way of doing this is with a tool called Wireshark. Now, Wireshark is awesome. We love Wireshark. It's a free open source tool. If you don't have it, go get it, learn how to use it. This is an excellent tool. The problem with Wireshark is that it simply lists all of these packets in order. So it just spits out a bunch of packets in a giant list and lists them top to bottom, and that's basically it. It's really difficult to visualize airtime usage with Wireshark, like who's talking fast, who's talking slow, who's repeating themselves. What of this is actual data and what of this is just management overhead? With Wireshark, we don't know. It's very difficult to tell what's actually happening. And that's when we decided to come up with IPA. IPA stands for I Packet Analysis because it's a visual packet analysis tool, and it allows us to visualize how much time all of these different devices are using up on the channel. Now, the first thing that we do with IPA is we shove everything into these multi-layered pie charts, and these charts show information in different layers. So let's break down each one of these layers. Now, the entire chart shows us how much airtime was used throughout the course of the airtime or the packet capture. So that's the total amount of airtime that was used. And then we can break this up and see who used that airtime and what were they doing. Now, the innermost layer shows us the name of the network. And so in this case, we can see that this innermost ring here is called Bronco Guest. That's the name of the network, and it used up about 2/3 of the total airtime on the channel. It used up about 2/3 of the total amount of time that was used on that channel. Now, we can have multiple access points that are part of one network, and so the next layer breaks it down by access points. We can see there's this one access point here that used up about half of the airtime on the channel. The next layer out indicates our client devices. How much time did our client devices use? And we can see that this particular client device used up about 1/3 of the total amount of time on that channel. Now, the final ring on the very outside shows us what type of frame that it was. If you remember your colors, you remember that blue is our data frames, and then orange and purple are our management overhead. So let's take a look at what we can do with that. With being able to see what types of frames were in use, we can see what is management overhead and what is actual data. So for example, all this orange stuff, that's all control frames. Those are acknowledgments. Those are block acknowledgments. That's RTS, CTS. If we look at the purple, that is our management frames. Those are our beacons. Those are our probes. We can say that beaconing, just an access point announcing that it exists, actually takes up a little bit of airtime. That takes up time on the channel. And then of course, all of the blue, that is our actual data. That's our data frames and our quality of service frames. So you can very quickly see what is management overhead and what is actual data. So now we're going to jump into a quick demo with IPA. We'll use IPA to identify top talkers. We'll see which devices are having slow and inefficient conversations. We'll see which devices are transmitting the most data. And then we'll identify some problem devices. We can pinpoint slow conversations that are eating up all of our airtime, and we can point out devices that are repeating themselves. We can also get expert tips from IPA. It has an expert tip engine that will generate, automatically tell us what's wrong with our network. We'll automatically see clients with excessive retries. We'll identify network settings that can hurt performance, and then we can export anything that we use in IPA to Wireshark, which turns IPA into a really powerful and easy to use filtering tool. So with that, let's go ahead and switch over to IPA. Now, what I've got here is I've got my trusty old Nexus 7 to 2.4 gigahertz only Android tablet. I keep it around specifically for these packet analysis webinars, and I've got it on channel 11 right now. So I'm going to start a packet capture on channel 11, and we're using the AirPCAP NX. It's a product by Riverbed. A product by Riverbed that allows us to get full packet capture in Windows. And now I'm going to start a throughput test on this channel. So now we are running. Something's wrong here. Let me fix it really quick. It's always in a demo that something breaks, right? Let me just restart my packet capture real fast here. So we're going to perform this throughput test. We're just going to use a simple one. We're just going to use speedtest.net, and we're going to capture everything that's happening on that channel, including the speed test that we run from the Nexus 7. Whoops, something went wrong with my AirP cap. It's always on a live demo. Give me just a second to see if I can fix this problem. We'll be right back. Okay, I think we're back in business now. So I'm going to go ahead and start that packet capture on channel 11, so you can see where we're capturing anything that's happening on the channel. Our file size right now is about 500 kilobytes. It's not very big. So now we're going to kick off our speed test, and now you'll see that file size is climbing very, very quickly. We've got about 10,000, 12,000, 15,000 packets, 20,000 packets. You see how quickly this stuff moves. Now, don't be too concerned about the invalid packets. Those are just packets that we weren't able to understand. We heard them, but we weren't able to verify that they were good packets, and so we discard those. It's very, very normal in packet capture for that to happen. So we just finished up our throughput test, so you can see that our file size has slowed down significantly. So I'm going to stop the packet capture, and IPA is going to crunch all the numbers and perform a bunch of analysis to figure out who used up how much airtime and who repeated themselves. Okay, so the first thing that I want to show you is here along the top, we've got the airtime over time graph. This shows us how much airtime was used at different points in time throughout the packet capture. So we can see here that when we started out, we were humming along at probably about 20% airtime usage, and then all of a sudden we had this spike where we went up to about 60% airtime usage. That is when we performed our throughput test. And then we had a bit of a break. You know, when speed test takes a bit of a break, it'll stop for a second, and then we see another spike here where we performed our second our upload test, where we uploaded as much data to the cloud as we possibly could. So that tells us what happened over time throughout the packet capture. Now, in the multi-layered pie chart, we can see that the biggest slice here, the key contributor to airtime on this was a network called MetaGeek. Imagine that. We go one more layer out, and now we can see our specific access point. This access point is called the plank. There aren't any other access points that are part of MetaGeek that are on this channel. That's good. And then if we go one more layer out, we can see that this activity, about a little less than 2/3 of the total airtime, was created by this ASUS device. Well, it just so happens that this Nexus 7 is made by ASUS, so I know that that is my device. Now, if we look at what it actually did, we can see that it spent some of the time with quality of service data, some of the time using block acknowledgments, and then some requests to send and clear to send. Now, we can drill down on any one of these layers by clicking on them, so I'm just going to click directly on the plank here. So we're going to focus on that network, and so now we have drilled down into it, and then I'm going to drill down further into our ASUS device here, which is my Nexus 7. Now you'll notice that in the airtime overtime graph, something has changed. We can see that there's the gray section up here and the green section. Gray is anything that we have filtered out right now. We have applied a filter simply by drilling down into this Nexus 7 and looking at it specifically. Anything that we have currently drilled down into or filtered into is colored in green, and then everything else is colored in gray. So now what we can do is, since we've drilled down into this, we can look at the retry rate. I can see here that my retry rate is about 12%. That's not bad. We're only repeating ourselves 12% of the time, which in Wi-Fi is pretty good. And I can see that we're very consistently using some nice fast data rates. About 30% of the time, I was able to hit 65 megabits per second. We also did see as little as 11 megabits per second about 35% of the time, but I'm not surprised about that, considering that this is 2.4 gigahertz and that it's a pretty noisy environment here that we've had to slow down a little bit for. Now that we've drilled down into this, we can go over to the Packets tab, and we can look at the conversation that happened between the access point and between the client device that we have filtered down to. We can see that constant process of sending data. So you can see where we sent our data, and then we received an acknowledgement, and then we transmitted a request to send, we received a clear to send, and then we sent our data and received our acknowledgement again. Request to send, clear to send, data, acknowledgement. You can see that process repeating over and over and over again. Now, one thing that I'm not seeing, which is really good, is I'm not seeing a whole lot of packets that are flagged as a retry. If we have to retransmit a frame, then we will see a retry flag there, and I'm not seeing a whole lot of those here. And that's a really, really good thing. Now, one way that we filtered down into this was simply by clicking on this device in the multi-layered pie charts. There are lots of other great filtering options built into IPA. For example, if you know the client vendor, in this case I know it's ASUS, you can type that in there. If you know the MAC address of the client device, you can filter down to that as well. So maybe for fun, we'll just apply some filters really quick. Let's just filter down to, we'll click on the SSID column here, and we'll just filter down to MetaGeek. And if you've ever used regular expressions in Wireshark, you just realize how easy this is. We could filter down to that specific client device. We can even filter down to different subframe types. This is that cheat sheet that I was talking about earlier. We could get rid of all of the management frames, and we could get rid of all the control frames and look just at data frames to see what was going on with those data frames as we were transmitting them. Now, once you've done all this, once you've applied some filters, I'm going to take out my control frame and management frame filters. Once you've done this, you can hit File and hit Send to Wireshark. And what that's going to do is it's going to take all those filters that you've applied, and it's just going to dump those right over into Wireshark. One thing that we believe here at MetaGeek is if it ain't broke, don't fix it. Oh no, one of my filters is broken. I updated Wireshark the other day and forgot to check and make sure that was working. I've had a couple of issues with a few things being broken there. I just need to go fix that. But now we have dumped all of those frames into Wireshark for deeper analysis. So if you really want to drill down into one of these beacon frames to see exactly what that access point is advertising, you can do that. No more having to use regular expressions in Wireshark. You can simply use the point and click ease of IPA. Now, a couple more things I want to show you. I'm going to go back to my captures here, and there's a capture I want to show you here called Lecture Hall. This is a nice, busy environment that was taken at a nearby university. And one thing I want to show you is that in IPA, if you go to the Analyze tab, this is our engine that will automatically warn you about issues on your wireless network. There's about 15 to 20 different alerts that we'll throw based on different conditions. One of my favorite ones is that we will automatically pinpoint any client devices that have a high retransmission rate. For example, this Samsung device here has a 100% retry rate, so it is repeating itself constantly. This Apple device has a 52% retry rate, and we'll actually call those out if we see those devices that are repeating themselves really often. Now, you can click on Learn More to learn more about what exactly that means, or you can hit too long, didn't read, to hide it again. The same thing goes, we've got some suggested solutions here, like, for example, there may be some Wi-Fi chipset issues here. You may have an outdated driver or something like that. You may have overlapping channel interference, adjacent channel interference, or you may have non-Wi-Fi interference that is causing those issues. So there's about 15 to 20 different alerts that we'll throw based on lots of different conditions, whether it be a security condition or a bad data rate setting or an 802.11b protection mechanism, things like that. We will alert you based on all of those different conditions in the application. Now, one of the tricky things about wireless packet capture is getting those packet captures themselves. The easiest way to do it is with the AirPCAP NX. This is a USB packet capture device by Riverbed. It does both 2.4 and 5 gigahertz. It's got a 2x2 radio on board, and it does 802.11a, b, g, and n, and captures directly into IPA. Now, if you're like me, if you have a Mac, you can use your MacBook Air or your MacBook Pro, or even your 2012 MacBook to get those packet captures. And a lot of the newer models, sadly mine's a 2012, so I don't get this, but anything late 2013 and newer, you get 802.11ac, and IPA can open up those packet captures. So be sure to check our knowledge base for a quick video that explains how to do that. Another great tool that you can use in OS 10 or Mac OS is the AirTool product by Adrian Granados, which is a free tool that you can get online that you can get those packet captures with. Excellent little tool. Really appreciate Adrian for offering that product. Just search for AirTool on Google and you'll be able to find that. You can also get them from other sources as well. If you're pretty good with Linux, if you're comfortable with the command line in Linux, you can get those with a normal Wi-Fi adapter in Linux, or some enterprise-grade access points will allow you to generate PCAP files. You just need to make sure that your PCAP file contains either radio tap headers or PPI common headers, and we'll be able to open those up. Just don't try to get a packet capture with a normal Wi-Fi adapter in Windows. Sadly, Windows strips out all of the management frames and the control frames and all of the data frames that are not destined for your MAC address, which makes packet capture in Windows kind of tricky, which is why the AirPCAP NX is a really convenient product to have. Okay, and at this time, I'd like to open up the floor for any questions and pass it back over to Julie. While we're answering those questions, be sure to grab this free Wireshark color profile. You can use all the colors that we have in IPA with Wireshark with that free profile. Julie?
Hi, Joel. Thank you very much for the wonderful presentation. It looks like we do have a couple questions for you. Let's see. I'm going to start off with, are there any dead zones in which your product will not pick up another specific product?
You know, I don't think I quite understand the question. One thing I can say is that this tool, since it is an 802.11 packet capture tool, we are only going to hear 802.11 activity. We're only going to hear Wi-Fi activity. With a packet capture tool, you're not going to hear any non-Wi-Fi activity. For that, you're going to want to use a spectrum analyzer.
Okay, thank you. No problem. Let me ask you this one. Of all of your products, which one is the most popular, or what do you sell the most, and what are the features that makes it so popular?
Ooh, good question. I think that our most popular one, it's kind of a split. We offer three main product lines. Insider is our Wi-Fi scanning tool. Channelizer plus Wi-Spy is our spectrum analysis tool, and then IPA is the packet capture solution that we talked about today. I would say that it's got to be an even split between Insider, our Wi-Fi scanning tool, and Channelizer plus Wi-Spy. Both of those are really popular. Maybe Channelizer is a bit more popular, maybe, but that's kind of a tough call to make.
Thank you. Let's see. I got another question here for you. Why are the packet counts different in Wireshark and IPA?
You know, I'd have to look into that more. I'm not sure why we'd be seeing different packet counts, because we're literally taking all those packets and just dumping them into Wireshark. Contact our support team at support.metageek.com, and we can look into that further. I'd have to really look into it to see exactly what's going on there.
Thank you, Joel, very much for answering those questions. I believe that's all we've got for today, and I'd also like to thank everyone for attending today's webinar. And if anyone has any further questions, please feel free to contact your sales rep or email us at sales@microcomtech.com. And if anyone wishes to view the products mentioned and shown today, please visit us at www.microcom.us. And remember, that this webinar presentation was recorded and it will be uploaded to our Microcom YouTube channel. If you would like to reference it again, you can view it again on YouTube. Thank you very much and have a great day.